All right. All right, great. So why don't we get started? So good, not morning, I guess officially afternoon. Good afternoon and happy Friday. I'm actually not used to teaching on a Friday, and I'm also not used to teaching, um, later than like 10:20, 10:30, 11 o'clock. So this is new to me. But today, what the plan is to spend no more than 10 to 15 minutes going over some front material concerning the PacMan Python code or Python PacMan code, whichever way you say it, and then spend most of the time of the period doing a so-called code walkthrough. Now, I've released on the Canvas site some code, and this code is sort of a sneak peek for project number two. And your focus on project two and throughout the course of the semester should be on the AI concepts. Again, I stress this is not a game design or a game engine optimization course or anything like that, right? There's a time and a place for that, and that time and place is not for this class. You're welcome to do that after the class, but please focus your time on the task at hand. And so ahead of time, I'll apologize for my voice. Certainly flu and RSV and all sorts of stuff is pretty bad this year. So I might just pause to grab a sip of water. One of your colleagues has already prearranged to be online for various reasons that are none of your business, right? So anyways, why don't we get started? Excuse me. So the administrative bits, of course, if you're not on the Slack channel, jump in, the water's fine. I will use Slack as my only means of communication with the class. Again, if you have questions, and usually when I say this, people still send me direct messages when they should send those questions about the class and the assignments. Please send your questions to the Slack channel. There are 40 of you in the class census, and I can't possibly manage individual messages from 40 people. And posting an interaction on the course Slack channel affords me the ability to force multiply, so to speak, so that others may benefit. Even the quote unquote naive questions, I promise you about a third of your colleagues had the same question. If you have something of a personal nature, please send me a direct message via Slack. You're welcome to also send me traditional email. I do get about 100 plus emails a day, and I'm not exaggerating. Every Friday night, I waste 3.5, 4 hours of my time going through lots of emails. So if you send me email and I don't respond to you, don't take it personally. Don't feel shy about sending me that email again and sometimes a third time because the AI algorithms will percolate that to the top, or more likely if you send it multiple times. Email is a serious problem. I wish we had other stuff in the university, but I choose to set up Slack for my classes because it best helps me to help you. So please make sure if you're not on Slack, join Slack today. Your expectation for this class is to be checking it regularly. Okay. All right. Project number one has been out. It's due this Tuesday night. Please make sure many of you haven't done it. Please just do the work. Jump in and just do it. Right. Because the purpose of this one grade scope is to get you used to the standard for submission for this class. So please get that out of the way. Subsequently, project two will be coming out in the near future, and the projects will grow in sophistication. So make sure you just jump on it and just get this done. Okay. All right. Any questions? No? All right. So why don't we get started? Excuse me. Is anyone familiar or is anyone not familiar with Pac-Man? Might be a little bit before your time. Oh, man, make me feel so old. All right. Well, Pac-Man was released in the 80s. I know, ooh, the 80s. Some of your parents probably were just born in the 80s, right? But nonetheless, it was released in the 80s, and it was a maze-based video game intended for the arcade. Do y'all go to arcades still? No? You just stay home and play on your console? Mhm. Well, I used to be a serious gamer until my daughter was born. 13 and a half years ago. So Dr. Coco T used to terrorize Xbox Live, but I don't anymore. It's been a while. I've hung up my controller pad. Anyways, so it was a maze-based video game developed for the arcade, and an arcade was basically a room with lots of video games in it, and it was a place where people, when I was a kid, you could gather with your friends, hang out, get snacks and stuff like that. So it's kind of like a social environment. And these video games took quarters. You know quarters, right? Don't make me sad. Quarter. Okay. All right. You put quarters in these things to play a game, and it was developed and published by a Japanese company called Namco, and its US-based distributor is called Midway. They licensed it from Namco. So here in the States, Pac-Man has sort of made a resurgence, these so-called retro games, among with Donkey Kong and Galaxy and Galaga and all those things. In the US, when you see Pac-Man, you usually see Namco. And these days, in electronic stores, they're selling these gaming consoles reproductions. And so the whole design of Pac-Man was to be cute and colorful, particularly to appeal to a younger audience. And many a kid from my generation kind of got their curiosity piqued about this new discipline called computing because of video games, because we all wanted to produce video games. And I remember my best friend from high school, we're still friends now, decades later. He's career U.S. Navy. We decided to create a video game, right? We called it Chasm Jumper. And it was sprite great based graphics using something on the Apple II series computer called page flipping. And, that's how we got our start. Computer science wasn't the big discipline then that it was now. It still was a profession, but the pervasiveness since then has only grown exponentially. And so this is what a Pac-Man game console looked like. And in an arcade, you would have music playing, you'd have all the sights and sounds, all the different consoles, and you'd walk up to the console and put your quarter in, and you could have two-player or one-player. And I can't remember, I think the two-player you took turns and not having two people play at the same time. And you would play, and if someone was already playing, you would put a quarter on the dash of this console to kind of signal that, I got next, right? Um, and so I spent many a quarter in this arcade game. And if you weren't very good, you spent a lot of money and you learned very quickly to get really good at it, turning over the game many times, right? So I miss those days. But nonetheless, this is what Pac-Man looks like. And this is the one by Namco. And one of the observations you'll notice is that for copyright reasons, they can't copy Pac-Man exactly for educational purposes even, right? But this is what the original Pac-Man looks like from Namco. And you have a maze, and these blue outlines, those are the walls. And that's the world in which Pac-Man lives. Pac-Man is this circular disk here, and this disk moves almost like a mouth chomping and eating. And so with the joystick, you control how this thing navigates left, right, up, or down. And as you navigate, these little white or beige dots on the screen, those are food pellets. And those food pellets, each time Pac-Man consumes one, you get some points. And so the goal here for Pac-Man is to eat all of the pellets. But confounding Pac-Man are some ghosts. And these ghosts lurk around this maze, and the ghosts are trying to kill Pac-Man. If the ghost touches Pac-Man, then Pac-Man dies. You lose a quote unquote life. But there's a saving grace here with this game. You see these larger circular dots. There are four of them on this particular layout in the upper corners of the board and lower corners of the board. And these are so-called capsules or power pellets, we used to call them back in the day. And when you eat a power pellet, you have some momentary period of time where the ghosts are scared. You eat a power pellet, the ghosts get scared. When the ghosts are scared, Pac-Man can eat the ghosts, and every time Pac-Man eats a ghost, you get points, and these points that you get are larger than the number of points that you would get from eating one of the food pellets. Okay. Any questions? No? And one of the things that you see in the Namco Classic Pac-Man, you'll notice here that this maze world is open here and here. That's a doorway. And so, whereas a doorway, if you proceed out one side of the doorway, whether you are the Pac-Man or a ghost, you're going to reappear on the other side. Okay? All right. Any questions? Now, in the original Namco Pac-Man, you also have fruit, and these various types of fruit will appear usually around here in the game. And if you eat that fruit, different types of fruit have different points values associated with it. Now, of course, in the Pac-Man for the course, that Python source, we don't have fruit, right? Again, and we also don't have doorways. It's just a closed maze for the purpose of implementing a number of AI techniques. Any questions? No? All right. And so I found the original, and boy, this is nostalgic. I just kind of remember those days. If I could go back, I would. This is the original Pac-Man, just to show you some of the game. Um, and once you put in your quarter, it would register that and actually start the game. Let me see if I have the sound up. 200 points for the first one, for second ghost, and the ghost flash. And the ghosts actively chase you. They get a little faster over time as well in the original Nameco version. This person's pretty good. It might have been me. And when the ghosts are eaten, or when they're scared, they change color. And once they're eaten, their eyeballs go back to the pen where the ghosts are reborn. And I'll just let it go to the goal configuration where um, all of the food pellets are eaten. Earned another life. There we go. All right. And of course, if Pac-Man, does anyone remember the sound for Pac-Man if the ghost kills you? All right. Okay. I haven't heard that very much. No. But nonetheless, this is the Namco version of Pac-Man, just to give, if you're not familiar, give you a sense of the gameplay, the design of the game, stuff like that. Now, this is the version from Python, and one of the observations you'll make is that there are no doorways. There are ghosts. The board and the ghosts look a little bit different because copyright is a real thing. Um, and there are also no pieces of fruit. We do have four capsules in the corners on the upper left and right, and the lower left and right. And of course, we have the Pac-Man that starts in the bottom center of the board. We have our food pellets, and just like the Nameco version, each pellet is worth some number of points. And as you eat the pellets, you accumulate points in the form of a score, which is reflected on the lower left corner, your left, of the game board. The ghosts also emerge from the pen and they swirl around and they try to follow you. If you come into contact with the ghosts, you die. But in this case, you only get one life. There are command line options when you run the game to specify more than one game, but there is no notion of lives that you go through as you play the game. It restarts the game each time from scratch. Um, there's no fruit. I think I said that already. And this is our Berkeley game. There's no doorways. I think I said that already. Okay. Any questions? No. There is an agent called the keyboard agent that you can run through a command line option when you're running the Python if you want to get a sense of how this approximation of PacMan works in practice. It is kind of hard to use on your keyboard. A joystick sort of has a nice throw to it. If you do your keyboard to control it, the keyboard agent, it asks you as the agent to make a decision or play an action. And that's done through the keyboard, or if you have a joystick, you're welcome to connect one. Okay, any questions? No? All right. And so the high level architecture of this game, it's a lot of code, right? As any game engine would be, there are a lot of moving parts within this, which is why I stress that your task in this course is to understand enough of it in order to complete the assignments. And in particular, that is all of the pieces of information that is presented to your agent's implementation, your methods that you will be implementing in order to solve the different problems for the projects in this class. Okay, I would highly recommend you save tinkering with it till after the class is done, right? Invest your time wisely using high utility, right? For that goal of doing as well as you can in the class. So we start out with our Pac-Man world. It's our maze-based game, and we have the simulation of it. And that simulation means many things. How that simulation is driven is with a class called game state. And game state is sort of where everything in Pac-Man lives as far as the food pellets, whether the food pellets are eaten or not, the position of the ghosts, the position of all of the agents in this game. Now, the agent is the primary entity that operates in the game. Pac-Man is one of the agents, and each of the ghosts is an agent. You can specify outside of the default how many ghosts you have. When the autograder is run, certainly it'll use the default for the four ghosts. Okay. But again, I say take the default and focus your attention and your investment in time and energy on the particular task at hand. Okay. So we have the game state, and the game state is used to control the entire simulation. And that includes both the configuration of all of the elements. And I forgot something I was going to mention at the beginning. When Alexander had mentioned 8 as the states, I was in my mind thinking percept configurations, but I said the word state, which is configurations of the whole board. So Alexander was right. It's not 4, it's 8. But nonetheless, the game state controls or represents all of the configurations or the state of the game, but it also applies the physics. And the physics has to do with two things. What happens when you make an action? How does that action change the environment or the world? And what is going on in terms of collisions? Collisions can happen when you make a move that would bump you into a wall, or you make a move that would change your position. Um, Physics also happens when you collide with a ghost. And part of that checking when you collide with a ghost is if the ghost is scared, meaning you've eaten one of those capsules, or if the ghost is not scared. Now, of course, when the ghost is scared, that particular state of the ghost is time driven. It's only scared for a prescribed amount of time, and then it goes back to being non-scared. And so all of this is controlled and represented and updated through this class called the game state. And inside of game state is another class called game state data. Game state data is where the actual data structures live that represent all of these things. And the game state provides the methods the accessor and mutator methods that interact with things from game state data. So it's highly recommended, actually, that you do not access game state data directly, right? You use those accessor and mutator methods that are inside of game state because it's presumed that's the entry point for interacting with that data. And so again, I'll stress, please do not modify the method signatures that are provided for you. You're welcome to add new method implementations, as well as certainly for the projects, provide the implementations for the task at hand. But please don't go tinkering with the method signatures for the code that's given to you, because that will certainly break the auto grader. Okay? All right. Any questions? No? And so, in addition to the game state, which is backed by game state data, we also have an abstraction of this world. And one of those abstractions, at least for project two, is called a search problem. And so search problem derives from game state and ultimately information in game state data, but search problem abstracts from it, in particular as a graph. And so one of the things to pay attention to when you're implementing for project two your search algorithms is to know the difference between when you're looking at game state versus when you're looking at search problem. Search problem is how you consider different alternatives, and it's a graph-based abstraction of what you see in game state. So in order to play search problem, you say game state, what happens if I went forward? And then you get a new version of game state and you abstract that as another node in a graph, and the edge is decorated with the particular action you took. Okay, so it's really important to distinguish between the two, because interacting with a search problem doesn't change the state of the game. Now, game state is a notional mutable copy, a mutable object, and as such, the practice is to create a new version, a deep copy of game state, and then do something with it, and then update the physics, right? And that update becomes the new version of the world or the environment in which Pac-Man and the ghosts live. Does that make sense? Any questions? No? All right. And so we start with the rules and simulation, the game engine, and we'll go through the main loop just in a few moments. And from game state, you get a search problem. And from search problem is where your implementation lives, i.e., your search algorithm. And what will happen is that you will be called to create an act or select an action, right? And inside of that selection of the action is where you get a copy of a search problem, you do some evaluation, and then you propose, hey, this is the best action to take. Does that make sense? All right. Okay. And so game state. Game state has a game state data object. That's where the data structures actually live, and game state provides the accessor and mutator methods to interact with it. It has a snapshot of the entire game. So that's the pellets, the pellet locations, whether they're eaten or not, the capsules, whether they're eaten or not, the ghosts, their locations, the ghost status, whether they're scared or not scared. And so it has a snapshot of the entire game. It also maintains the score, the food, and the ghosts. I just alluded to that. It applies, or where the rules and the physics are are invoked, and this includes both the transitions in space for all of the agents operating, as well as the collisions, be that collisions with one another, the Pac-Man and the Ghost, or collisions with the environment, namely the walls, and also the game inter-engine interactions. And so some key methods, get Pac-Man position, which is obvious from the name of the method. Get ghost states, okay? A state can include position and also for the ghost, whether or not they're scared. Get the food, generate successor, is win or is lose. Is win and is lose checks, returns Boolean, and it checks whether or not you're in a win or a lose situation. Lose means you've collided with a ghost and you're done. That was called the kill status. Win means that all of the food pellets have been eaten and the board is clear. Okay. Any questions? No. Now, generate successor. That's the key method where you choose an action and it kicks off all of this interaction in order to make the right update to produce the next state of the game. Okay. Any questions? No. All right. Of course, a search problem is an abstract state space. It presents your state as you traverse through different states of the world, as expressed through game state, and it provides a graph-based abstraction. It maintains those pieces of information it needs. It also checks for legal transitions. If you try to move forward and there's a wall, it rejects that transition and replaces it with a no-op or stop. It's used by your search algorithm. Some key methods: get start state, is goal state, get successors, and get cost of actions. For certain of the algorithms we'll be looking at, so-called search algorithms and heuristic algorithms and stuff like that, you're going to be evaluating cost of an action. Okay, and we'll talk about that next week. When you call get successors, it's really important to distinguish between get successors in the search problem and generate successors in the game state. Generate successors in the game state is going to update your game. Get successors in a search problem is going to evaluate what the child states are when you make a single move. And that single move corresponds to an edge for each of the actions, followed by a child node, which is the resulting state of that game by taking that action. And so the two are different, right? Search problem takes information from game state, but when you call get successors on search problem, it doesn't alter the game state. It evaluates what happens as a consequence of things. Does that make sense? All right. Any questions? No? All right. So in a game simulation, what will often happen is in a loop with some other stuff, some checking. There's time penalties because if you take too long, that'll decrement from your points because in this implementation, they want you to make a move and do things quickly, right? So in the main loop, it'll effectively on the game state object called game state generate successor, and it'll pass it an action and also an identifier for which agent it is. And when you do that, it applies the physics, updates the score, checks the collisions, returns a new game state, and updates the display. Okay. And so, what exactly are the physics? It's the rules for things that can happen, how the world updates as a result of the action that you take. And when we talked about situated agents, you're in the environment, and not only does the environment change of its own accord, and from the perspective of the PacMan agent, the ghosts are moving, right, and pellets are getting eaten, but it also reflects the state, reflects your position in the world. And so here we have the score, the collision game state, I'm sorry, the physics, how the world updates when you take an action, and this is triggered by the game engine, which is just basically a loop, right? Main loop. There are various other helper classes in play. One is called PacMan rules, and that's where all of the requirements of a PacMan are. How it moves, how it changes its position in terms of XY coordinate when you take a particular action. It maintains the direction in which you're pointing in addition to when you make a move. The ghost rules encodes all of the things for the ghosts, how the ghosts move, whether they're scared or whether they're not scared. Now, certainly this ghost rules, it doesn't maintain a copy of the key data structures. It refers back to game state, which refers back to game state data. So they really, really try hard, the authors of this code, to separate concerns in terms of maintaining data structures in one place, the game state data, versus the accessors and mutators to that data structure versus how you enforce the rules. Does that make sense? Any questions? No? And of course, the physics includes this collision and scoring logic, as well as this continual check for a loss or a winning configuration. Okay, movement. One agent moves one cell on every quote unquote turn. And so the Pac-Man is an agent. Each ghost is an agent. The standard in the code is Pac-Man is so-called agent zero. It's always the zeroth agent in the list of agents. And a turn refers to an opportunity for a single agent to do something, to select an action. And so for this movement, it's limited to north, south, east, west, and stop. Illegal moves, as I said before, are overridden, replaced with stop, and movement is discrete. So this is a discrete domain. We're not going to do continuous because we don't have time for a continuous. Um, with the turn taking, it iterates through those lists of agents, starting with PacMan. So PacMan always makes the first move and then goes through each ghost. Again, you can specify as many ghosts as you want. I don't know what the limit is. It'd be kind of crazy to have like 30 ghosts, but you can specify that. I never checked if there's a bounds check on that. So PacMan is called Agent Zero. And when you talk about search depth, you count the plies, not the move. Each ghost gets their own turn, and a turn is a single agent's opportunity to act, and that includes if it's a stop action. So even saying I'm not going to act is your turn. And so you call get action for one agent. And in fact, when you implement your agent, you're going to be filling in the details of the get action method for the assignments. And so you call get action and you apply the physics in order to update the resulting game state. Okay, any questions? No? All right. And so around everyone gets a turn. You count turns, um, not rounds. And the depth in terms of search trees, which we'll talk about next week, is the number of turns or so-called plies. So you'll see that vocabulary used, which relates back to the book. So when you're debugging things, um, some guidance is to set a breakpoint in PacMan rules apply action and Ghost rule apply action because that gives you the context of the decisions being made for each of the agents, the two flavors of agents, right? Um, when I was younger, well, I got my license well into my 20s, right? I was always taking public transportation or riding my bike, and getting hit by a car twice, commuting to work by bike kind of changes your perspective on biking. But I used to, when I first got my car, fill the tank with gas, pick a direction, and just drive, right? And so we're going to do a similar thing with the code, just have a scenic drive through the code to see how some stuff works, look at the call interactions, and look at some of the key parts, keeping in mind, and that's how to understand how things fit together, not that you should go in and try to change or improve upon the game engine or the code. Again, those opportunities are always there after the end of the semester, in your summer, when you're not taking classes. Okay? All right. Any last questions before I switch to the code? No? Okay. All right. So let me stop the share. And I'm probably gonna share the screen. Let me make sure do not disturb is on. I always get telemarketer and spam calls only when I teach for some strange reason. All right. So let me bring down the slides. And I have my copious notes here. Let me minimize that. And so what I'm going to do is I'm going to bring up two things. Let me go back to Zoom. And I'm going to share the desktop so I don't have to manage switching between windows. Okay, let me hide meeting controls. And let me minimize this window. Put this over here. Is that okay? Let me bring up a console window and post it on the Canvas site for this lab session is a zip file containing all of the code that you're going to see here. And so I'm going to run the PacMan game from the command line. And it's really helpful to use the command line, but I'm going to walk through PyCharm when I do the code walkthrough, but I just want to first bring up a version of the game. And so this is the keyboard agent version of the game. And so I'm controlling it now. The keyboard is a little bit of an inefficient, the ghosts turn white, not blue and white. Um, so you can navigate around north, south, east, west. You can eat the pellets. The ghost will get scared. Let me see if I can eat a ghost. No, I'm not that fortunate. Ah, there we go. Oops. All right. So, anyways, once you get killed, the game is over. You only have one life to live. Sort of, what happens. All right. So you notice I get a score. I could run the auto grader. No, I'm not going to do that. When you run the auto grader, it's going to take your agent entry points for get action. It's going to exercise them against a bunch of test cases and then return the scores to suit. So let's go ahead. I did the keyboard agent, but I'm going to run. Let me just run pacman.py with the help turned on. And so when you say pacman py run the Python dash h, it'll display this help. And it gives you a bunch of the different options. And there are very many of them that you can have for a game. So here, I'm going to run PacMan using a layout called the original classic version of PacMan. And then the agent I'm going to use is so-called left turn agent. And when left turn agent selects very simple actions, it takes a left turn wherever it can. Okay. So let me bring that up and you notice it's taking all left turns. It doesn't clean the entire board. Sometimes it looks like it's actually doing something rational, but it's just taking simple left turns at every junction point where a left turn exists. And it'll just go right back around and sweep the same way. And so here, what will happen in your assignment, you'll be changing the program -p, which is the type of agent, and it's going to be your planning agent that uses some of these graph-based search methods that we'll talk about next week. Okay, any questions? No? All right. So let me switch to PyCharm, and I have that up already. And I'm going to start with the pacman.py, and we'll take a scenic drive through the code. Can you all see that? Is that that's not too small? To be young eyes again, huh? All right. Okay. So we start out, and one of the things that's important, I guess this is an IDE thing, you still have to give it the command line arguments. And so in whatever IDE you're using, there's going to be a way to specify command line arguments because we're running it from the IDE and not from the command line. And how you select certain things like the type of layout, and there are many different layouts, is through these command line switches. If you're curious about what the layouts are, if you go into a directory called layouts, you will see a bunch of .lay files. And a .lay file defines the initial configuration, both the food, the ghost, and the PacMan. And so if we looked at, well, let me cat it because I don't want to accidentally add to it. Original classic. Let me hide that. Hide meeting controls. It's just ASCII art. And so it reads the ASCII art and it sets a wall wherever the percent sign is, ghost wherever the G's are, Pac-Man wherever the P's are. A dot is a pellet, and it looks like an O is a capsule, right? To make the ghost scared. And so each one of the layouts that you have here, you can specify as a command line option with that -L switch. Okay. All right, because it's hard to memorize all the layouts that are coming with the game. But I wouldn't spend any time trying to create a funky layout. Again, you should invest all of your time and energy on the particular task at hand. And so here, just like I had from the command line, I'm going to run the layout for the original classic board, which we just saw, using the left turn agent. And so get action is going to be the get action method for the left turn agent, which will just go through a bunch of checks. If a left turn is available as a legal action, take the left turn at every turn for this agent 0, which is the PacMan. Okay, so I'm going to go ahead and I set a breakpoint inside of the main entry point. And the first thing it does is processes the command line options and then goes ahead and calls run games. So let me start the debugger, hide a little bug here, and execution is now at this breakpoint. One of the things I dislike about the layout, I never bothered to try to change it, is that the controls for the debugger for single step, step over, step in, step out, this small little bar here really needs to be a bigger bar up here, complete. But that's just my nitpick. Um, so I'm going to step into run games, and inside of run games, you'll notice it does a bunch of checking about the graphics, create the new game, set up the display, and it calls game.run. Okay, so if we continue execution here, let's go inside of game.run, and game.run is in, I think it's game.py. Let me see. It's agent configuration. Yeah, it's game.py. Yeah. All right. So you start out, you initialize the display. Okay. Step over, and you notice the frame for the window pops up. Let me move that over so we can see it. Maybe I should make that a little smaller. I got the beach ball. That wasn't good. Oh, all right. Yeah. All right. Because it's paused. Um, I set the number of moves. Now I loop through all of the agents and I select all the agents, giving each a turn, starting with agent zero, which is the Pac-Man. Okay, so then this is there are parts in this code where they're kind of doing introspection, right? They're looking at modules and directories, and then they're looking at methods and in modules and all sorts of stuff to look to link the command line for running an agent method with a switch to actually things in the code. So let me continue. Let's go down here. We loop through, uh, select the agent, and so let's see, register initial state. Um, let's see the agent type. We have a random ghost. Okay. So it initializes the ghost first before the Pac-Man. All right. Let's see. It sets some timer information. So that's another ghost. So let's see. Starting index. Okay, this is the main loop. So now fetch the next agent. Let's see which agent this is. It's the left turn agent. And so the left turn agent is the agent for the Pac-Man that it has been set up with through the command line options. So let me look at my notes. So we're going to look for the simulation where we call generate successor on the game state object. So let me go down here a little bit more. We make a deep copy of the game state. And so often what happens, you make a copy of the game state, and then you do something to the copy, and then you replace the game state with the copy after you do all the physics, check the physics, and update the display. So we make a copy here, and we set some timeout information, and then here, agent get action. So that's where we're going to call in ultimately to your code. So let's step inside of agent get action. And you notice here in pacman agents.py, we have a class called left turn agent, and left turn agent, which was what was selected as the agent program, it's get action method. And so get action is where it's saying, okay, it's your turn. You tell me how you're going to move. And so it starts out, let's step over, get the current state. We look to see if we have a valid action, and that action returned is going to be going west. Okay. So now we append the move history because we want to do a replay. This can do a replay. Um, and then we check generate successor. Generate successor says, okay, now go ahead to that game state for which we did a deep copy and go ahead and do all the updates. That doing of the updates corresponds to checking the physics, looking at the validity of the move, checking the rules, both for the Pac-Man rules and the Ghost rules, looking at the food status, all of those things, and then updating the display. So let's look inside generate successor, step in, and generate successor is inside pacman.py. And so pacman.py, the first thing in generate successor is it's asks, is this a losing state or a winning state? Because you just stop if that's the case. So typically the pattern is that you always check for the win-lose state before you do anything else. Okay, so now we take a copy. This is a shallow copy of game state. And you notice every time it's going to do something to game state, it makes a copy. All right. So now we check to see if it's agent zero. Agent zero is the Pac-Man. And you notice here, if it's the Pac-Man, the difference is it uses the application, apply this action. You know what action Pac-Man is going to has selected. Go ahead and apply it to the rules for Pac-Man in order to make sure that the game state is appropriately modified per the rules of the game for the Pac-Man. If it's not agent zero, agent 1 through 4 with the defaults, agents 1 through 4, the first position, which is second in the array, through the fourth position, those are the ghosts. So Pac-Man is always agent zero. Okay, so we go ahead and we check it is agent zero. We update what the eaten status is for all of the pellets in the environment. And then we go to apply action against the Pac-Man rules. You have two things, that state, which was the game state that was shallow copied, and you have the action that was selected by that agent. Any questions? No? No questions? Make sense? All right. So let's go into Pac-Man rules. And Pac-Man rules says, okay, well, let's yeah, I'm in Pac-Man rules. It's easy to get lost in this code. Um, let's get determine if it's a legal action. Okay. Um, it is a legal action. We're going to get the state for this particular agent. Let me, and then once we know our action, which is north, south, east, west, direction to vector, it takes that command north, south, east, west and converts it to a two vector. And what that two vector is going to do is it's going to add to the x component and add to the y component the suitable value in order to change the xy coordinate of this Pac-Man. And so if you're pointing up and you say go north, your y coordinate is either going to be added to, was it added to? I think it's added to, no, subtracted from. Otherwise, the y coordinates can be added to. And so this convert to vector is going to return a two vector, which is used to update the XY coordinate from this token north, south, east, west. So if I go and I highlight over vector, in this case, it decrements from the X coordinate where it was before it took this action or is to apply this action. Um, once it does the action, the X coordinate is going to decrement by 1. And so you get that vector, and then you go ahead and you tell the configuration through its mutator method to go ahead and create the successor using this vector, which was translated from the north, south, east, west token, right? And so this is part of the physics that goes on underneath the covers. And so then we get the position, we check what the nearest point is, we're going to do some distance checks, and then we want to know whether we should consume what's there, right? So we do that consume, and we're back to this call for the Pac-Man rules. And then we check the time penalty. Are we taking too long? And we want to check death if we've eaten a ghost, right? Or if we should die as Pac-Man because the ghost is not scared. So we do that, and then we update our score, and then we return the resulting game state. Okay, so now once we've done all of that, that's the simulation. That's all of the important changes to data structures that have happened. Wow, it's almost one. And we go ahead and we update the display. So this is our initial position for the display. It started out with the layout, and that layout had the Pac-Man in the bottom center of the screen. I believe 00 is the bottom left corner in XY coordinate. And the first thing it did was go west. It's a left turn, right? Well, it's pointing that way, so you can't take a left where there's no hallway to go down, right? So it's just go west. And when you said action is west, it coerced that into a vector of -1, 0. It added that to what the XY position was for the Pac-Man, and then it applied those physics to either eat the pellet or die if it ate a ghost, checking the ghost states and the ghost positions. Does that make sense? All right. So then we're going to um, I forgot what this does. All right, so now we're going to go to the next agent. And this next agent, because it's now agent one, let me check. Yeah, that's going to be a ghost. Again, the Pac-Man is always agent 0. So we're going to go through again. Game is not over. We're going to select the agent from the list of agents given the agent index. We're going to do a deep copy of the game state, and we're going to mute a couple things, check some timeouts, and now we're going to say agent get action. Now, that agent get action, that's going to be for one of the ghosts. And so you notice here inside of ghost agents.py, we're in the get action method for the ghost agent class. And so I'm not going to go through all of this. Let me just chooses from a distribution what the action should be. Where am I? Generate successor. Okay, generate successor. So we select the action from the agent. The agent, which was the ghost, selected east, and the ghosts are currently in the pen. So when we update here the display, you'll see one of the agents move. That was the blue one. The eyeballs kind of, you run so fast, your eyeballs stay fixed, right? Um, let me see. All right, so let me loop through that a little bit. All right, so let me just set a breakpoint um, inside of, I think it was PacMan search agent. There we go, search agent. Um, Let me just set a breakpoint here. No, it was left turn agent. Where was it? Go west. Oh, I lost where I was. All right, let me just continue the step and then I'll set it the next round through. All right, generate successor, update the display, agent index. That's now 4. That's that last ghost. And next agent index. No, that's 4. Let me loop through that. Let's go back to the PacMan. And mute successor, update display. Okay, so this next agent index, since it's modulo arithmetic, should be back to 0. And let's just go ahead and set a breakpoint inside of the get action method for the PacMan agent instead of every agent that runs. So I'm going to step in. That was in PacMan agents. Okay. And this was left turn agent. So I'm going to set a breakpoint there. And let's just run. And this will go through each of the 5 agents, the PacMan and the 4 ghosts, because I'm setting the breakpoint and get action on the left turn agent. And so as you can see, each agent it goes through does that update and checks the physics, and the display updates accordingly. And so what will be really important is the agent code that you're given, the command line will change to select that particular agent function associated with the search agent. And for project number two, you'll be implementing different types of search algorithms using the search problem abstraction, which is a graph, and that abstraction is done for you. Okay? All right. Any questions? Whew, it's a mouthful. Any questions? Is this helpful? So please don't be afraid of the debugger. I encourage you, if you have 10 minutes here, 20 minutes there, just do a walkthrough, run the game, get used to how its semantics are, start looking at the code. But I would kind of leave the game engine part aside and just focus on how these different pieces hook in to your agent program that's called the get action. Okay? All right. Any questions? Any last questions? No? Again, I've also posted resources on the course Canvas site that are not the only ones, but some links to some YouTube content with some intermediate Python and some advanced Python. Some stuff that you'll see in the code, of course, when they do abstract classes and base classes. They also do lambdas, which are temporary nameless functions. They do a bunch of different things in Python that you may or maybe not have covered in other classes. So please avail yourself of any Python resources. I'm leaving that up to you to do that. And I know certainly data structures is in Java, right? It's not in Python. Okay. So well, Java is a little more sophisticated than Python for object-related stuff. So it's not terribly difficult to translate. You can have abstract classes, you can have base classes, yeah, inheritance. Java doesn't do multiple inheritance. That's why the interface exists in Java. But nonetheless, Python implements a lot of the same stuff Java has, annotations and things like that. Okay. So please feel free to take a look at the code. Project number two will be this exact code given out. And in that assignment, when it drops, you'll be given the code or the names of the Python files and the functions you'll be editing, knowing that you will not be changing the method signature for the existing code, but you're free to add whatever other implementations you deem fit. Okay? And that will also be using the auto grader, right? And like I said, for the first project, um, you basically get to determine the grades you get, right? How awesome is that? Assessment will be validation, and you can run it as many times, but please make sure when you go into grade scope that you activate the grade that you want, right? Because all I'm going to see, I'm not going to look at, if you did 50 submissions, trying it, wonderful. All right. But I'm not going to look at all 50 of your submissions looking for the best grade to activate it. That's your job to activate the grade that you are satisfied with. And so there's no link to Gradebook in Canvas and AutoGrader. I thought there would be. So that's going to be a manual process. I do use Gradebook, and I program Gradebook with the syllabus weights so that at any time throughout the course of the semester, if you want to know how you're doing, you can see it. But the one caveat with Gradebook is that the grading intervals for the different grades is different in Gradebook from what it is in the syllabus. So always rely on those intervals in the syllabus, not what Gradebook displays. Okay. All right. Any questions? No? And so this is supposed to be fun. Everyone looks so serious, maybe because it's Friday and I'm probably between you and what you're planning to do for your official weekend. But just like that, we're at the end of the first week. Semester's 15 weeks, 1 week down, 14 weeks to go. It'll happen faster than you think. Thank you. And to those of you not here, I know who you are. All right. So interesting. But thank you for coming. The first step to success is showing up, right? All right. So have a great weekend, and I'll see you all on Tuesday.